Hello, welcome to Key in Motion's course on understanding electricity and electronic devices. This is our 6th class. As usual, we're going to start by reviewing what we saw in the previous class and some others that are going to be useful to the contents that we're going to see in this one. On the previous class, class number 5, we studied electricity and magnetism. And we saw some of the applications like the clamp meter, electromagnets, and other applications like DC motors, relays, solenoids, and all that stuff. Also, on a previous class, we studied AC and DC, what's the difference between those, and we're going to use those concepts as well as LEDs. In today's class, we're going to study diodes, which are very related to LEDs. So for today's class, we have capacitors, diodes, and rectifications. Those are the 3 main topics that we're going to be covering today. So let's start with capacitors. Capacitors are devices that have 2 terminals, and the main characteristic of those is that they can store electric charge. And the amount of charge is proportional to the voltage between the terminals and the capacitance. The capacitance is the main parameter of a capacitor. So putting the above point in formulas, it's Q equals C times V, or Q is the charge stored, C is the capacitance, and V is the voltage. And capacitance is measured in farads. The symbol is F, and 1 farad equals 1 coulomb over 1 volt, okay? So how is a capacitor made? A capacitor is built as 2 metallic plates, like this one, one conductive plate or metallic plates, and separated by a non-conductive material, right? Like this one here. When you build a capacitor like this, the capacitance is constant epsilon times the area, that's the surface of each of these plates, divided by d, which is the distance between the 2 plates. So this epsilon is called the dielectric constant, and it is a function of the material here. Depending on the material we use, we can have a higher or a lower epsilon here. So if we want to build a capacitor with a high capacitance, we have a few options. We can use a material, a dielectric material between the plates with a high dielectric constant, or we can increase the area of the plates, or we can reduce the distance of the plates. In practice, capacitance is also increased by adding several layers. So that construction is shown here, where we have several layers connected to one terminal and several other layers connected to the other. So what we're doing here is pretty much adding up the area of all these layers and creating a higher capacitance for this capacitor, okay? So how does a capacitor look in real life? So it will look like something like this. So it can take very many different forms. And these are the symbols for the capacitors. So it's symbolized as the 2 parallel plates that we saw for the construction. And some capacitors are polarized. So they have a positive and a negative terminal. The negative terminal can be symbolized in different ways, like this way with a curved plate, this way with like a plate kind of surrounding the other one, and this one with a solid plate, and as compared to this one that it's just outlined, okay? 1 farad, which is the unit of measure for capacitance, is a very high capacitance. So you will not find capacitors of 1 farad. Actually, you will. There's a recent technology that is that allows us to build what we call super capacitors, and those are measured in farads. But up to recently, the most you could get was thousands of microfarads. So capacitors are usually measured in microfarads, nanofarads, or picofarads. Capacitors above 1 microfarad are usually polarized like this one and are usually electrolytic aluminum capacitors. This is a capacitor of 100 microfarads. And as you can see, this is the negative terminal. This is the negative sign here, and it is next to this terminal. Also, this terminal is shorter and the positive terminal is longer. I would not go by the length of the terminals, but I would go by what's marked on the case. When you purchase a capacitor, the two main values that you want to specify are the capacitance, and as in this case, 100 microfarads, and 25 volts is the maximum voltage that this capacitor can withstand without being damaged. Also keep in mind that when you have a polarized capacitor like this one, you have to use it in this polarity. You have to ensure that this terminal has a higher voltage compared to this one. If you reverse the polarity, you can damage the capacitor even if we have a much lower voltage than 25 volts. Maybe with 5 volts, if you apply the reverse capacity, you would be damaging this capacitor. Okay, very good. So let's have a look at how we can use a capacitor in a circuit. Let's consider this circuit up here. When this is a double throw single pole switch, right? That allows this plate of the capacitor to be connected to the 5-volt power supply or to the 10 kilo ohm resistor. The negative side of this 100 microfarad capacitor is connected to the negative terminal of the power supply. When we connect the positive plate of the capacitor to the positive side of the battery or the voltage source, the capacitor is gonna charge, right? Current is gonna flow, current or charge is gonna flow from the battery or power supply to the capacitor, and it's gonna be stored over here. So the capacitor is gonna charge to 5 volts. Let's assume we move this switch to the middle position and in such a way that this switch is not touching the left or the right contact. At that point, the 5 volts are still on the capacitor. So the capacitor stored the charge that, that flowed from the power source into the capacitor and got charged to 5 volts. If we leave this in the middle, the charge is still stored there, and the capacitor is still charged with 5 volts. Now, when we move the switch to the right position, we establish a path or a circuit for the charge that is in the capacitor to flow, right? So remember, this is charged positive, so it has excess of positive charge or lack of negative charge, really. And this negative terminal has excess of electrons. So when we connect the switch to this side, we are providing a path for the charge stored in the capacitor to flow through the resistor. And that's actually what's going to happen. The capacitor is going to start discharging, and the voltage is going to start to go down. And the voltage is going to start to go down according to this equation here. V, the voltage on the capacitor, is going to be equal to V0, which is the initial voltage on the capacitor, in our case 5 volts, times e to the negative t over tau. T is the time, and tau is a time constant that we're going to see in the next slide. This particular circuit has a time constant of 1 second. So we can see that the voltage on the capacitor starts lowering, starts decaying from the initial 5 volts to around 1.7 volts at the mark of 1 second. And after 3 seconds, the voltage remaining is very little here. So looking a bit deeper into that time constant that I was mentioning on the previous slide, the time constant is calculated as R times C, and it's measured in seconds. If you have resistance measured in ohms and capacitance measured in farads, the resulting here, the resulting unit here, it's going to be seconds. More commonly, you would have a resistance measured in kilo ohms and capacitor measured in microfarads, and kilo ohm times microfarad is millisecond. If we go back to the previous slide, I have 100 microfarads times 10 kilo ohms. So 100 times 10, it's 1000, and micro times kilo is milli. So this is 1000 milliseconds or 1 second, okay? So after 1 tau, tau is R times C, and again, it's gonna depend on the value of your resistor and your capacitor. The voltage will drop to about 37% of the initial value. So 37% of 5 volts is about 1.8 volts, 1.85. So here, after 1 second, which is tau, the voltage is here at 1.8, 1.85. After 5 tau, so in the previous slide, that would be 5 seconds, because tau was 1 second in that particular example, it will drop to 1%, and it is considered that it discharged completely. So keep in mind, this is 3 seconds and the capacitor is almost discharged. If we keep going for 2 more seconds, we're gonna touch 0 volts here. Okay, let's see an example of how we can use all this information to do some calculations. An RC or resistor capacitor circuit where C, or the capacitance, equals 10 microfarads and the resistor equals 4.7 kilo ohms is discharging from an initial voltage of 10 volts. How long does it take for the voltage to reach 3.7 volts? Okay, we have 2 ways of solving this problem. One way would be going back to this equation here that shows V equals V0 times e to the negative t over tau, and solve for t, right? And we have V, which is the 3.7 volts, V0, which is the 10 volts, and tau, which we're going to be calculating in a minute. Then solving for t, we know exactly how long it will take. But remember that after 1 tau, after 1 time constant, the voltage drops to 37% of the initial value. So in this case, if you have a look at this, 3.7 volts is 37% of the initial value of 10 volts. So the answer is that this is going to take 1 tau. And because tau is 10 microfarads times 4.7 kilo ohms, which is 47 milliseconds, we can conclude that it will take 47 milliseconds to discharge from the initial 10 volts to the 3.7 volts. And 47 milliseconds is the same as 0.047 seconds, okay? So again, it is 1 tau because the voltage that we're interested in is 37% of the initial voltage, and the time that it's going to take, it's 1 tau, which is R times C, 4.7 kilo ohms times 10 microfarads. So how long does it take to discharge completely? Well, on the previous slide, we also saw that we can consider it completely discharged after 5 time constants or after 5 taus. In our case, our tau is 0.047, so the time it will take to discharge completely is about 0.235 seconds. All right. Now, the same way a capacitor can discharge over a resistor, it can also charge through a resistor. Like in the example I showed you before, when the switch was on the left position, the capacitor was connected straight to the power supply. Now we are connecting it through a 10 kilo ohm resistor. This 10 kilo ohm resistor is going to limit the current that goes into the capacitor. So the capacitor is not going to charge instantly, but it's going to charge following a curve like this one. V equals V0. This is not V0. In this case, it's going to be VF. It's the final voltage times 1 minus e to the negative t over tau. So if you solve this equation, you will end up with a curve like this. Time constant is exactly the same. It's calculated as the value of the resistor times the value of the capacitor. In this case, it's 1 second. So after 1 second, this is going to be charging to 63% of the final value in this case. Okay. And again, after 5 time constants or 5 tau, it will reach 99% of its final value, and we can consider it that it is fully charged. Okay, so we're going to start with diodes now. If you want to take a 5-minute break or review part of capacitors, this is the time to do it. We'll see you in a bit. Okay, welcome back. So let's study a bit about diodes. Diodes are devices that allow current to flow only in one direction. For instance, this is a symbol of a diode, and this is a voltage source, and this is a resistor. We know that without the diode, current would flow in this direction. Okay. Now, the diode, this triangle here, is pointing in that direction. So it means that is the direction where the diode is going to allow current to flow. So current is going to flow here in this circuit. Okay. Now, if we go to this circuit over here, the positive side of the voltage source is here. So current is going to try to flow this way. But because we have the diode and the triangle of the diode is pointing in that direction, which is the opposite of what the circuit is going to try to make the current flow, current's not going to flow in this direction. Okay, so no current is flowing in this circuit, and the same on this one. No current is flowing in this circuit, right? So I start on the positive side, come through the resistor, and the current cannot flow anymore. So there's no way this circuit is being closed or completed. So current doesn't flow here either. So I spoiled a bit of this slide on the slide before, on the previous slide, but this is a symbol of a diode. This terminal is called the anode or the positive side, and this one is called the cathode or the negative side. This is what a diode looks like. It's usually, it can look in different ways, but this is one of the most common that you're going to be seeing. So it's like a black cylinder with 2 terminals, and the cathode is usually denoted with a little band here, usually in silver color or some different color. Okay, let's see how we can use what we're learning about diodes to solve some circuits using diodes. When I talk about solving circuits, I mean getting voltages and currents along the circuit and different points in the circuit. Something to keep in mind is when current is flowing, the voltage drop in a diode is about 0.7 volts for a very wide range of current. So even if you don't know how much current is flowing through the diode, you can approximately say that the voltage drop is going to be 0.7 volts. And this is similar to what we studied with LEDs, remember? Depending on the color of the LED, you would have a voltage drop that could be like 1.5 volts for a red LED to 2.5 or 3 volts and maybe higher for blue LEDs, okay? So the same way we had that in LEDs, we have about 0.7 volts for regular diodes. So let's try to solve this circuit here. So we have a voltage source of 5 volts, and we know that the voltage source is going to try to make current flow in this direction from the positive to the negative side. And because of the way this diode is here, we can assume that current is actually flowing in the circuit. So how much current? Okay, let's start solving this circuit. Assuming this is ground, you would have 5 volts here, correct? And we know that the voltage drop on the diode is going to be 0.7. So the voltage here is going to be 0.7 less than 5. And that's going to be 4.3 volts at this point. So once we know that we have 4.3 volts here and 0 volts here, we can know how much current is flowing through the resistor by Ohm's law. So that would be 4.3 volts divided by 1 kilo ohm, and that is 4.3 milliamps. Just keep in mind, if the diode wasn't here, you would have 5 volts on the resistor and you would have a current of 5 milliamps. So the diode here is not perfect, right? It's not, even when it is allowing the flow of current, it's not like a wire. So you have, depending on the circuit, you may have to account for the 0.7 volts or something like that that you're going to be losing on the diode. Now let's have a look at this other circuit. It's the exact same circuit, only the diode has been reversed. And we know that current's not going to flow through this circuit because of the orientation of the diode. The power source is going to try to make current flow in this direction, but the diode is going to oppose current flow. So no current is going to be flowing here. So what are the voltages and currents? Well, the current is 0 because the diode is not allowing any current to flow. And we have 5 volts here. And if we apply Ohm's law here, 0 current with 1 kilo ohm, that means 0 volts here. Okay, so those are the voltages here. And so the voltage drop on the diode here, because it was conducting, it was 0.7 volts. The voltage drop on this circuit here, because it is not conducting, it's the same voltage as the power source. So the voltage across the diode is 5 volts, or strictly speaking, it would be negative 5 volts, right? Because voltage is usually specified with this terminal positive and this terminal negative, but because the voltage here is higher than this one, that would be a negative voltage. Okay. How can we check a diode with a multimeter? Well, on the multimeter, we have a diode check function, which is this function here. And this is similar to what we did when we tested LEDs. So how do you check that? You put the multimeter in the diode check function, and then you connect the positive or red terminal from the meter to the anode and the negative to the cathode. If this is the correct polarity, the multimeter will show the voltage drop at the current, which is going to be around 0.6 or 0.7 volts. Because the current from the multimeter is very low, we're getting a voltage that is a little bit below the 0.7 that I was mentioning previously. When the diode is damaged or destroyed, you would see a much lower voltage here if the diode ended up being short-circuited, probably less than 0.1 volts. So you can assume that the diode is damaged in that case, or this would go out of range and would show like zero conductivity in this direction. But as long as you measure somewhere between 0.4 and 0.7, that diode is good. So if you want to specify a diode, the two main parameters that you have to specify are the maximum forward current and the maximum reverse voltage. For instance, you can specify a diode for 1000 volts, 1 amp. So when the diode is conducting, if you have a current higher than 1 amp, the diode's probably going to get damaged. And if the voltage, the reverse voltage is beyond 1000 volts, the diode's going to start conducting. This is something that is actually done on purpose on some circuits and with some special diodes. But normally you should not exceed this voltage in your circuit. Basically, that's the maximum voltage that the diode is going to block in reverse. If you put more than 1000 volts on this diode, the diode will allow current to flow. Okay, we're going to start with rectification, which is one of the main applications for diodes. Rectification is to convert AC into DC. So why would we want to do that first of all? Well, the main reason is because power distribution to the home is done in AC. So we studied that in our second class. Whenever you say you have 120 volts on your outlet, on your household outlet in North America, for instance, that is 120 volts AC or alternating current. Remember that this means that the polarity alternates 60 times per second or 50 in Europe. But most circuits, most electronic circuits and devices require DC to work. So at some point you have to convert the AC voltage from your outlet into DC. Okay, and if you remember that diodes allow current to pass in only one direction, they are prime candidates to do this rectification. So remember, polarity alternates many times per second in AC. So if you allow only one polarity to pass, which is what a diode does, you are getting into rectification already, okay? So let's start with this circuit here on the left. This is called a half-wave rectifier. Let's assume we have a 9-volt power source, but AC. Remember, this wave here means that this is an AC source. So it doesn't have a positive and a negative terminal, but the polarity alternates from positive to negative many times per second. Here in the blue trace, we have how the voltage varies. So it varies from 0 to some maximum here. This is about 13 volts, okay? We'll get into that value in a few slides now. But the important thing is it goes up on a positive value. That would be positive here on top and negative on bottom. And then it starts going back to 0, and then it crosses 0 and it goes to a negative polarity. On a negative polarity, it means that the top's going to be negative and the bottom's going to be positive. Now, if we have a diode here and a resistor, when this side is positive, the diode is going to allow current to flow through the resistor and back here. Now, when the polarity is reversed, the diode is going to block the flow of current. So the current is going to try to flow in this direction, but the diode is not going to allow that to happen. So if we were to measure the voltage on the resistor, when the diode is conducting, we will see the voltage on the resistor closely following the voltage from the AC source. There's a difference between this maximum value here and the maximum value here, and this would be your 0.7 volts that you're losing on the diode. So if you have here, say, well, if this is 10 and this is 15, this would be 12.5, and this one here would be a bit below 12, like 11.8. So that's the 0.7 volts that you lose on the diode. Anyways, when you continue with the cycle down to 0 and to the negative side, on the negative side, the diode doesn't allow any current to flow, so the voltage across the resistor is 0. So if you have a look at the voltage across the resistor, the polarity is always the same, only the voltage varies, right? So it varies from 0 to a maximum of 11.8 or so, then it goes back to 0, stays at 0 here, and then goes positive again. So the negative side of the wave has been clipped or eliminated. So this is called a half-wave rectifier because it allows only half of the wave to go through, right? It blocks the other half, and then it allows this half of the wave to go through, and so on. Okay, so this is one step forward because the polarity, it never goes negative, but the voltage goes down to 0. This is not something that we want. So we have to figure out a way of improving this circuit. And this is done with a device that we already studied, which is a capacitor. And that brings us to the topic of filtering. So the output of this half-wave rectifier can be smooth if we put a capacitor here. Remember, a capacitor acts like a tiny rechargeable battery, right? So if we were to charge this capacitor during the positive cycle, when the diode conducts, and then when the diode does not conduct, we could discharge this capacitor on the resistor, okay? So this is how it would look like. Basically, we have the blue trace here, which is the AC voltage source. Then we have the red trace, which is the half-wave rectifier output. And then we have the green trace here, which is the output of this circuit. So how does this work? Well, like I said, when the output from the diode raises, it charges the capacitor up to this maximum value. When the voltage starts to go down on the blue trace, right? The capacitor will hold the charge here for a few milliseconds in this case. This scale is in milliseconds, right? In about 5 milliseconds, it reaches the peak, and then the voltage here starts to go down on the anode of the diode. And the capacitor is going to hold the voltage for a little bit. So the diode stops conducting at this point when the input voltage starts to go down. Remember, in the previous circuit, the diode conducted all the way until the voltage was 0. But now, because we have the capacitor is holding the voltage here. So this reached 11.8 or so volts. and then this one started to go down. So the diode is in reverse, like I said, and not allowing the capacitor to discharge to this side. So the capacitor discharges to this side, and it's going to discharge slowly if the capacitor and the resistor are sized correctly. So maybe following this slow discharge. So by 16 milliseconds or so, 16 or 17 milliseconds, when the next cycle comes up, the capacitor did not reach 0, but it reached pretty much half of the voltage, say 7 volts, okay? So now we have a voltage that never reaches 0, but oscillates between 7 and 11 or 12 volts, right? So this is getting closer now to a steady DC. Remember, what we want to get from here is a steady 11 volts or 10 volts or something that works better. So how can we even improve this further? Well, enter the full wave rectifier. So remember, on a half wave rectifier, the negative side of the wave was wasted. So it would be nice if we could flip around the negative side and make it positive, right? So in this case, even without a capacitor to filter the output, this would be 0 volts, but only for a tiny fraction of a second, instead of being 0 for a full half cycle. Okay, so a full wave rectifier is something that actually exists and does this thing here. This is what the circuit looks like. Let's try to understand how this works. So let's start with the positive half cycle. That's what we're going to be calling when we have positive over here and negative down here. So when we have positive here, the current's going to try to flow this way, right, from the positive side. And then it's not going to flow this way back through this diode, because this diode is reversed. It's going to flow, it's going to block the flow of current. So it will flow this way, following this red arrow. Again, once we reach this point, it cannot flow this way because that would be against this diode. So it's going to flow through the resistor. After it flows through the resistor, it goes back here, right? It cannot flow back here because, again, this is at a higher voltage, right? So we just lost voltage when we went across the resistor. So this is at a higher voltage, so it's not going to flow this way. But it's going to flow through this other diode and then to the negative side of the battery, okay? So voltage goes through this diode, through the resistor, and then through this diode and back to the negative side. So what happens when the polarity gets reversed? So when the polarity gets reversed, I have positive here, right? And current flows through this wire, then it cannot flow through this diode because that would be in reverse. But it flows through this diode, again through the resistor. And if you were paying attention, the polarity on the resistor remained the same, positive on top and negative on bottom. So current flows from top to bottom on the resistor. After it flows through the resistor, it goes through this wire and then to the negative side of the source through this other diode. So again, remember, in the positive cycle, that's when, a positive half cycle, when this was positive and this was negative, current was flowing through this diode, through the resistor, and through this diode here. Now that the polarity has been reversed, current is flowing through this diode, through the resistor in the same polarity, and then through this diode back to the source. So this circuit is called a full wave rectifier, and it makes current flow through the resistor, doing both the positive and negative half cycle of the wave. And that's why it's called a full wave rectifier. Now, what happens if we add a filter, a capacitor here to this full wave rectifier? Well, it is not surprising that the output is going to be smoothed out. But there's a difference with the previous circuit that we saw on the filter on the half-wave rectifier, because now we have the capacitor charging here and then slowly discharging through the resistor. In the half-wave rectifier, the capacitor had to hold the charge until this point pretty much here, right? Because we didn't have this positive half cycle here. Now, because the full wave rectifier will provide us with our half cycle, with our positive half cycle here, with the same capacitor and the same resistor, this capacitor does not discharge all the way to the previous voltage because we're recharging it sooner, right? We have this half wave here that arrives sooner, and that will recharge the capacitor again. So instead of going down to about 7 volts, which is what we had on the previous example, this goes down to only 10 volts. So a full wave rectifier means that you can use a smaller capacitor here and obtain the same quality of DC, or that you can use the same capacitor and get a better quality of DC. Okay. That configuration is called a bridge, right? Whenever you have 4 devices of the same kind connected like these with 2 inputs on the top and the bottom and the 2 outputs on the left and right side, we call that a bridge. So a bridge of diodes is a full wave rectifier. They are also called bridge rectifiers. And full wave rectifiers are very common, and diodes are cheap, right? So they are manufactured as a pre-made package. And just to make it clear, these are only the diodes and not the capacitors. You still have to add a capacitor to these to get a filtered output. But this is what they look like. They are usually, well, they come in all different kinds of current. These are for fairly high current. I would say this is probably for about 3 amps. And this is probably good for like 50 amps or maybe 100 amps. So you have 4 terminals, 2 for AC and 2 for DC, 1 marked positive and 1 marked negative. Now remember, this is only the rectifier. You have to put a filter and maybe something else for this to be providing pure DC at the output, okay? Now let's talk a bit about peak voltage and RMS voltage. And this is something that maybe I should have introduced with when we started talking about AC, but when you talk about pure AC, this is not really that important. But when you start talking about rectification, this is important. So remember on the 9 volts AC circuit that I showed, and when I showed the wave, I showed that it reached peak values of around 13 volts. So let's try to see why is it that is happening. So if you have a look at the wave, the voltage is currently changing. So there's not a single fixed voltage. In this area, the voltage is close to 0. In this area, the voltage is close to 12.7. So if you were to connect these to a resistor and try to figure out how much power that's going to be delivering. Let's say you connect these to a 1 ohm resistor and you want to know how much power it is delivering. Well, the power here, the average power I'm talking, right? So, and that's, the power is varying instant to instant. So the power here is going to be 0, and the power here, it's going to be 12.7 volts squared divided by 1 ohm. That is probably like 150 watts, something like that. Anyways, we would have to do the calculation. But what I'm trying to say is power varies from 0 to 150 watts and then back to 0 and so on. So what is the average power that we are delivering to that resistor? Well, if you make the calculations and the math beyond that requires some calculus, some integration of the power over one cycle, you would end up with an average power of 81 watts when this is connected to a resistor of 1 ohm. So that means that this wave that has peak voltage of 12.7 volts behaves like a DC voltage of 9 volts. 9 volts squared, that's 81 divided by 1 ohm, that is 81 watts. So when the AC voltage that we have here can deliver the same power that compared to a DC voltage of 9 volts, we say that this wave has an RMS voltage of 9 volts, okay? And whenever you connect a voltmeter, an AC voltmeter to an AC source, what that's showing you is the RMS voltage, not the peak voltage. So if you were to measure this with a multimeter, you would be measuring 9 volts, not 12.7 volts. Okay? And the relationship mathematically between the peak voltage and the RMS voltage is the square root of 2, which is approximately 1.41. So if you want to know what the peak voltage is on your outlet, 120 volt outlet, you multiply that times the square root of 2, and you will end up with something close to 170 volts. So your peak voltage on your outlet is 170 volts, but nobody talks about that. That everybody talks about the 120 volts that is the RMS voltage in your outlet, okay? So after rectifying and filtering, the output voltage will be closer to the peak voltage of the AC. So the rectified voltage will increase by a factor of about 1.41, okay? So if we go back a few slides here, right? This was a 9 volt source, and the voltage here is oscillating between pretty much 10 and 12 volts, right? So the peak voltage is about 12 volts, right? And if you were putting a higher capacitor, it may be able to hold the voltage a lot closer to the 12 volts that you have here. So you started with a 9 volt AC source and you ended up with a 12 volt DC voltage. Okay, so, and that is because the rectified voltage, it's going to be closer to the peak voltage, and therefore it will increase by a factor of 1.41 compared to your AC RMS voltage. But also have to keep in mind that you're going to be losing some voltage on the diodes. So if it is a half-wave rectifier, you will be losing 0.7 volts. If it is a full-wave rectifier, because current flows through 2 diodes, you're going to be losing 1.4 volts. Okay? And that concludes our class for today. So let's do a quick review of what we studied today, okay? We studied capacitors, and the main property of capacitors is that they can store charge. We can think of them as little tiny rechargeable batteries that will last charge not for a few hours or minutes or seconds, but more in the range of, well, maybe some seconds, but more in the range of milliseconds or maybe less, depending on the circuit. They're usually measured in microfarads, nanofarads, or picofarads, because 1 farad is a huge amount of capacitance. And higher values, and by that I mean above 1 microfarad or so, are usually polarized. So you have to pay attention to which terminal is positive and which terminal is negative. And they can be used to build time delay circuits, right? We saw that we can charge them slowly with resistors, or discharge them slowly with resistors as well. So those are going to be used in time delay circuits, or could be used in time delay circuits. Then we studied diodes. The main property of diodes is that they allow current to flow in one direction only, which is what we call forward bias. So when voltage, when diodes are forward biased, the voltage drop across them is about 0.7 volts. And diodes are specified by the maximum forward current and by the maximum reverse voltage that they can block. And the last thing we studied was rectification, which is the conversion from AC to DC. We studied the half wave and the full wave rectifiers. The full wave is more efficient because it makes use of the negative side of the wave that otherwise would be wasted on a half wave rectifier. Then we saw how filtering or adding a capacitor can improve the quality of the DC output, make it smoother and closer to a true DC output. And then we studied the relationship between RMS voltage and peak voltage. And that produces an increase of the rectified voltage, but by a factor of 1.41. But remember, you are going to be losing some voltage on the diodes. And that's all for today. Next class, we're going to see voltage regulation, which is something that can get us even closer to perfect DC when converting from AC. And we're going to start looking at transistors and how they can be connected and what are some of their applications. So thank you for attending this class, and we'll see you next time. Bye.